The objective of this video is to establish conditions on magnetic field behavior at the interface of air and iron, or in other words, low permeability and high permeability regions. And the second objective is to introduce field diagrams within the context of flux tubes and reluctance elements. So we've arrived at the final analytic approach that we're going to be using to calculate fields, and this approach is a hybrid of the magnetic equivalent circuit approach and the FEA flux diagram approach that we've been talking with using our FEA. And so this approach unifies both of these. It's as I said, it's kind of a hybrid of the two, and we're going to be using it more for gaining physical understanding of our system than we are for actually making calculations, though you certainly can make calculations. But it provides a way to tie things up and show the uniform view of the way that fields distribute themselves, and it gives us more physical insight into our system. So let's start with the first objective, which is going to be used in order to make the second objective possible: establishing conditions on the magnetic field behavior at the interface of air and iron. And so suppose that we have some big piece of iron which has a relative permeability that is much, much greater than 1. And that means that compared to our air gap, which has a permeability equal to naught, we can pretend that our iron permeability is approximately infinite. It's just so large compared to the air gap permeability. And we've previously talked about this meaning that our field, our H field in our iron is equal to 0. So if our iron permeability is infinite, our H field is approximately 0. And so what we're going to do is we're going to evaluate Ampere's law along the interface of our air region and our iron region in order to establish conditions on H and B. And we're going to pick an Amperian loop very deliberately, like this. And so the height of the Amperian loop in this direction is dy, differential y. And we're going to pick dy to be infinitesimally small so that we're evaluating H directly on either side of this surface. And it's going to have some width that we'll call delta x. So I'm numbering these sides so we can distinguish them. We've got 1, 2, 3, and 4. And if I evaluate Ampere's law around this path, I'm going to pick delta x and dy to be small enough that we can assume that H is constant and comes outside the integral. So we get an expression for H like this. And on the right-hand side of this equation, we have the surface integral of j.ds, and there is no current enclosed. So there's no current within here, so therefore that integral is equal to 0. So if we look at this expression, we've said that dy is infinitesimally small, so these terms do not contribute. They're equal to 0. Now we can also cancel out our delta x's, and we can conclude from this that hx1 must be equal to hx3. So that is our field in this, our H field in this direction, above and below the interface. And recall that hx1 is equal to 0. That's what we had set up here. So this tells us that hx3 must also be equal to 0 at that interface. So the H field in the x direction in air is 0. And therefore, our B field in the x direction in the air is also 0, because B is equal to mu times H. And this tells us that the flux lines are perpendicular to the interface. So we've got magnetic field coming down like this, and it has to exit this interface exactly perpendicular to the surface. It cannot go like this or like this. That is what we have just found out, that it has to exit that interface exactly perpendicular. And this is an important conclusion. So that means that if we have a tooth of our stator, and we're solving for the field that's flowing through our stator, our field can exit that stator tooth like this at all points, but it cannot exit like this. Let's now consider the same thing, but we're going to put some current within that Amperian loop. We're going to put some current right at the surface of our interface. And the current that we're putting there, it's a linear current density, which means that it's infinitesimally thin. It means that I is equal to the integral of a dot dx. It's just the integral along a line is the total current. So this is an imaginary thing, but it's a concept that we're going to be using on occasion. And it's convenient for this derivation. So we rewrite Ampere's law. Only now, integral j dot ds is equal to the integral of a dot dx, which is equal to a times delta x, because that's the width of our path. And if we write out if we evaluate Ampere's law for the H field, we get the same thing as before on the left-hand side, but now the right-hand side is equal to a delta x. And this delta x is going to cancel with these other delta x's, so that we get this expression. So we know hx1 is 0 because h is 0 in the iron, which means that hx3, h in the x direction in the air, is equal to a, which means that b in the x direction in the air is equal to mu naught. And this is our second important observation. So if there's no current present, there's no current at the interface, then b in the air is perfectly perpendicular to the interface. And if there is current present, then b has a component that is in parallel with the interface. It's in parallel with the current. All right, now let's use these in what are called field diagrams. But before we can use it, let's define what a field diagram is. And a field diagram is what you produce with your FEA tool when you show the flux lines. So we've previously talked about using FEA to show lines of constant vector potential and commented on how those are the boundaries of our flux tubes. I'm now going to draw that for some generic region down below. So each of these lines that I'm drawing is a flux line, and I'm just doing this arbitrarily. So if you remember, we said that our flux lines were the boundaries of our flux tube. There's no flux that can cross a flux line, because the flux lines represent values of constant vector potential. Please refer back to the previous video if this is unclear. And on top of this, I'm now going to draw lines of equal potential. And so it's possible to do this because we know that no flux crosses these flux lines, so we know that in some sense they're flux tubes. And so between any two flux lines, there has to be a line that we can draw that is of equal magnetic voltage or equal scalar potential. And again, I'm just drawing this arbitrarily right now, but there's a unique solution for any given field. And each of these lines represents a certain magnetic voltage value, while each of the black lines represented a certain magnetic vector potential value. And if we draw this right, what we do is we have each of the lines be at a fixed interval. So there's a fixed delta A between each of the vector potential lines, and a fixed magnetic potential difference between each of the equipotential lines. And so if you recall, we previously derived how you can calculate flux through a flux tube or between these magnetic flux lines. And we had two options. One, we either evaluate b dot dA or b dot ds, and if b is constant, we can say it's b times our area. Or we can evaluate it in terms of the vector potential as the vector potential difference between the two lines times the length into the page. And we're set up to do this very conveniently. The way we've drawn this right now is that each of these flux tubes has the same delta A difference. So effectively, we can quickly evaluate the flux that takes this channel as just being that delta A times our depth into the page. And we can use this for a practical calculation. We can find the reluctance of each of these flux tubes. So if you recall, reluctance is equal to the difference in our magnetic voltage divided by the total flux that flows to the tube. This is just Ohm's law for a magnetic equivalent circuit. And so each of these tubes that we've shown up here, because they have the same delta A, each of the tubes is going to have the same reluctance. However, the interesting thing is that each of the tubes may occupy a different amount of physical space. So while the difference between A3 and A4 that is A4 minus A3 is delta A, and that's the same as A3 minus A2. The physical difference on our plot, the physical distance in the x and y coordinates, is clearly larger between A4 and A3 than it is between A3 and A2, at least at this location right here. And so we can use this to calculate several quantities of interest. We can find the total reluctance or permeance between two equipotential surfaces. And to see what I mean by that, consider that we want to find the permeance or the reluctance between this surface here and this surface down here. This entire here is one flux tube. And then of course we have a second flux tube over here and a third flux tube to the right of that. And each of those flux tubes has a certain reluctance. So these really look like reluctances that are appearing in parallel. This translates to a reluctance network that looks like up here, this node is at voltage UM4, and this node is at voltage UM1. And so the reluctance between those two nodes is just the parallel combination of those three reluctances. And since all of them are in fact the same, it's just going to be reluctance by 3. So we can calculate the reluctances between two equipotential surfaces, and then we can calculate the total flux that takes each of those flux tubes, and we can use that total flux to calculate the magnetic field everywhere to approximate it. Because remember, magnetic field, or flux density, is just flux divided by area. So that built up how we can use field diagrams to calculate reluctances in fields when we're given a field diagram handed to us. That is, I told you what this diagram looks like, and then now you have the tools to take that diagram that's been given to you and calculate reluctances and fields. However, next let's talk about creating our own field diagram from first principles. And so we're specifically going to employ the information that we developed above about magnetic field being either perpendicular or having a parallel component to an air and iron interface. And then we're also going to employ the boundary conditions that we previously talked about. So we're going to consider the following example from your textbook. And in this example, we have a stator pole, which we're told that the whole pole, it's iron, and it's at equipotential. So we're assuming mu is approximately infinity. And then we have a rotor surface, which is also at equipotential. And here's where the physical insight comes in. Our textbook tells us that this line is a line of symmetry. So basically our model stops at this point as far as what we're modeling. The physical system continues. And on this line, we're going to be imposing a symmetric boundary condition, or a boundary condition based on symmetry. And that condition is that all flux is perpendicular to this surface. And we accomplish this by putting a condition on the derivative of our vector potential. Because if you recall, By is equal to the partial derivative of our vector potential with respect to x. And we want to make that 0. And this boundary condition was called the natural boundary condition. And by doing this, we effectively create an equipotential surface. We extend the rotor equipotential to go now vertical. And then over on the other side, we're again given some information based on physical insight of our system. And that is that we have flux being parallel to the surface. So this is again a natural boundary condition, and it's a condition on the derivative of A. And so that ends up being the boundary of one of our flux tubes. So we know that the entire stator pole is at a magnetic voltage, we'll say UMS, and our entire rotor surface is at a voltage of, say, UMR. And so between these two lines, we have a potential difference. And we'll divide that up into some number of areas. So let's say in our case, we'll draw this as 4 different potential levels. And starting from the right side, just given the geometry of our structure, we know that the potential differences must distribute themselves equally. So there's no reason, just given the uneventful nature of the right side of the diagram, the spatial distribution of the potentials must be equivalent. And then as we follow this geometry around, our top potential is going to tend to track the rotor surface. And I haven't done a great job of drawing this because on this side as well, we should have the equal spatial distribution. So on the right side, we had an equal amount of delta y between each of the equipotential surfaces. And on the left side, we should have an equal amount of delta x between each of the equipotential surfaces. So you can see that if you were very precise, you had a protractor and a compass, you could draw this much cleaner and get something that is close to a real solution. And now we'll draw our flux lines. And in this case, we're going to draw them in gray. And so starting on the right side, we see that our flux lines should all be parallel. And that is, we know that they exit and enter the high permeability surfaces perpendicular to the surface, and there's nothing to cause them to contour in the air gap. So we're drawing these all as perpendicular lines until we start to get some curvature. And when we have curvature of our surface, again, they have to exit the surface perpendicular, but they will arc down to enter the next surface perpendicular. Each of these lines represents a flux path. So we have a flux tube here, we have a flux tube here, and then in between them we also have flux tubes. And each of those flux tubes is a reluctance. And so we can use these observations about flux entering and exiting high permeability surfaces perpendicular, and then our physical insight into the system to impose boundary conditions. So we had to understand the nature of magnetic fields in our cross-section in order to employ these boundary conditions of the equipotential surface over here and the flux tube over on this side, the boundary of the flux tube over on this side. And by doing this, we were able to draw a fairly precise fields diagram that we could, again, use to calculate our total flux, our permeability, and our fields everywhere. I'm saying it this way, the reluctance to the total air gap, but I mean the reluctance between two equipotential surfaces. But I'm saying it this way because what we're actually interested in calculating is the total reluctance that we're going to see when we try to force a flux to cross from our rotor to our stator. And we can use that as a reluctance element in a magnetic equivalent circuit, or a system of flux tubes that represent our stator teeth, our back yoke, and whatnot. But we can take this hybrid approach where we use our fields diagram to calculate some reluctance components in that magnetic equivalent circuit. And then we can, of course, also use this to calculate the fields everywhere. Okay, so that concludes this lecture. And to summarize, we have established conditions in the magnetic field behavior at the interface of low permeability and high permeability materials. And we've summarized this as that when flux lines enter and exit a high permeability material to go to or from a low permeability material, they have to do it perpendicular to the surface of the high permeability material, unless there is a surface current density or a linear current density on the surface of the high permeability material. And then we introduced field diagrams and showed how they can be used to construct flux tubes within a cross-section, and how those calculations can be used to calculate the total reluctance of a complex system. And this reluctance can then be linked into some kind of broader magnetic equivalent circuit. We showed a manual way, we gave an example of a manual way to calculate and to draw these fields diagram, which is based on an example in your textbook.